All right, how y'all doing? This is where I want to do a circular motion problem, and so I want to talk about flying an airplane. If you fly an airplane, you you've probably had this experience if you've ever been on one of how the plane turns. It doesn't turn the way you turn a car. It rolls over. It tilts its wings. Someone draw a plane from the back, and what you get is here's a plane, there's the tail section, and the tail has a little bit of something on it. And then here are our wings. And so what this is going to do is try to go that way, where that is into the page, and then turning left. So let's say this is a 737, has a maximum takeoff weight of 80,000 kilograms. And one of the things they tell you is just in general, you should not tilt the wings more than 30 degrees from the horizon, or your passengers get really scared. Really, really scared. So, what we want to know is what is the radius of this turn? If the plane is flying at 600 miles an hour is, let's say, 275 meters a second. That's a good, nice round number. All right, so this is probably a reasonable thing. Planes, if you've ever been on one, when they land, they often are coming from somewhere, and the runways are lined up not in the direction they're going, and you have to turn. We can try to figure out what's going on. So from above, here's our plane. Right? And it's going like this. And we want to know the radius. So this is one of those things where we're going to do free body diagrams. Now, this is one of those things where I'm showing you a problem that seems completely unrelated to what you're doing, but you do have a couple of these in the homework. It's not an airplane. It is the conical pendulum problem, and if you have a banked turn. Basically, there's a class of problems where the physics looks really similar despite the forces being completely different. So we draw a free body diagram. The plane clearly has a bunch of weight, and there is drag, but it's out of the page, and we're going to ignore that because it doesn't cause the plane to turn. And because we don't want to deal with three-dimensional stuff, that's a pain in the butt. There is a lift force. The air hits the wings and is pushed downwards. The force on the air is down. The reaction force on the plane is up. All right, it's a third law of force between the plane and the air. And so it's at an angle here. All right, so we have a right triangle here. This angle is 60 degrees. There's a right angle that I've drawn in there, and so there's this little tiny angle in there that is 30 degrees. That's 30 degrees. So there's upwards and downwards components. This one I'm drawing in is L sine theta. This one is L cosine theta. Now, we don't know what the lift force is. And I'm already jumping out way out on a limb and saying a lot of other stuff I've just Googled. I don't know what the lift force is, and I wouldn't trust myself to know. The important thing is if you're not told something, it probably cancels out in some way. So we're going to proceed through the problem. We're going to write out Newton's second law for everything. So the sum of the forces in the y direction will take up as positive y and right as positive x. So the sum of the forces in the y direction, well, I have the part here, that is lift times cosine theta. That's in the positive direction. In the negative direction, I have the mass, the weight, which is m times g. And this is a nice level turn, so we have no acceleration. Then we have the sum of the forces in the x direction. This is the bit where we have an acceleration, and it is L sine theta. But that equals the mass times the acceleration in the x direction, but that is the mass times v squared over r, because it's moving in a circle. This is, a sub x, the acceleration in the x direction, is the bit making it go in the circle. So from this upper one, we get that L cosine theta is mg, and from this one we get L sine theta is mv squared over r. Can we solve for that? Well, we have two unknowns. R is the thing we're looking for, and L is this lift force we don't know. But we have two equations. They're different equations, so in principle we can solve. And what I'm going to do is write this slightly differently. On past work, I'm going to put L sine theta is mv squared over r. L cosine theta is mg, and I'm going to divide these two equations. So when I divide them, I get L sine theta over L cosine theta. Well, that has to equal the division on this side. mv squared over r divided by mg. And lo and behold, the lift force divides out. And so does the mass. The mass does not matter in this, oddly enough. So we have this thing. If you remember your trig, this is tan theta. And on the other side, we have v squared over rg. So we can write this out as r is v squared over g tan theta. And now we can just check what that is. I'm running out of space here. So v squared over g tan theta is r, and that equals 275 meters per second squared over 9.8 meters per second times tangent of 30 degrees. So 275 squared divided by 9.8, and we divide by tangent of 30. And what we get is 1.3364. And now we got to figure out the units. We have meters per second squared on the bottom. We have meters squared per second squared. So a bunch of stuff cancels and we're left with meters. And this is a 13 kilometer turn. That's the radius of it. And that's our R. That's what we wanted. So that's a lot, right? That's a big thing. But the thing that I want to focus on is this free body diagram, which I want us to draw again. Lift, weight. So there's other things that share this free body diagram. if I have, let me get a clean sheet of paper here. There's too much milk. So we have a lift and a weight, but you could have the conical pendulum problem. All right, there's our vertical, there's our pendulum. This has the free body diagram of tension and weight. You could have a car driving around a track that's banked or a banked curve. There's an angle theta. And then here's our car. Right. So driving around this curve, you would have a normal force and a weight force. You ever seen those toys where you put a, like at the, at a museum or something, where you put a quarter down a ramp and it starts spiraling around this funnel? And obviously it takes your money, but if you have a free body diagram like this, it's going to have a formula that looks like something like those. Or maybe V is square root RG tan theta, maybe something like that. So when you see problems like this, right, you might jump and be like, oh, this is the thing I want because it's got R in it. But you have to kind of realize that when we drew the free body diagram here, there was no one force that caused the thing to go in a circle. Instead, it was actually this component here that caused it. And that's what this statement says. But you needed the other one to figure out what's going on. You need to do the free body diagram. All right, you need to go through all the steps regardless of what's happening. So, all right, that was a good problem. Let's do another problem. Why are curves banked in the first place? Well, curves are banked in the first place because imagine trying to make a turn without the banking. All right, so you have a car. Now this is the view from the back or the front. So there's our tires. Then there's the body of the car, and it's going to make the same sort of turning, but it's on flat ground. So the view from the top is car goes that way, turn with some radius. But it's flat. So the free body diagram for this, so let's give it some numbers, 1,000 kilograms going 20 meters a second. And let's say that the radius here is 100 meters. Right. So, maybe what we want to figure out is what is the frictional force going on here to make it turn, because that's what's going to happen. We're going to have a free body diagram that has a normal force and a weight force. And we're going to look at that and say, well, none of that can make the car turn. What makes the car turn? Well, it ends up being a friction force into the turn. Right? So we have this friction force. We can try to figure out what it is. But we can also ask what's going on. Why is it a friction force? Well, ask what happens when you exceed this friction force, when you're no longer going on the turn, well, you skid off the curve. Your car goes straight instead, which means it increases R. So at your maximum frictional force, you're going along this curve, and if you have to increase it, you can't. That sounds like this is a static frictional force. And that's kind of important. If you look at how a wheel rolls, it does not, the point that touches the ground doesn't move along the ground like this. It gets picked vertically up and put vertically down. All right, so we'll look at, say, this point. What's going to happen is it's going to roll down, it's going to touch the ground, and it's going to come back up. All right, is when it's over here, those points are the same when this thing is moved over like that. So, the wheels, the point that's touching is not in motion. It gets picked up off the surface and a new point is put down. So, anyway, what we want is this maximum frictional force. Well, that's the thing making it turn in the circle. So, this sum of the forces in the circle, in the x direction, is the frictional force. That's mv squared over r. And so we have numbers. This frictional force is 1,000 kilograms times 20 meters per second squared divided by 100 meters. So it's going to be 4,000 newtons. Right? We're going to cancel that out. So we'll have 10 kilograms, and units will cancel, give us newtons. So it's going to be 10 times 400 is 4,000. Hooray. We solved that one quick. Didn't even touch the calculator. But it's all in trying to figure out what's going on here, in the free body diagram. Anyway, that's what I wanted to do. That's kind of your circular motion is all going to be stuff where the motion is in a nice flat circle, or it's in a vertical circle, or it's on a banked track. So we should also talk about vertical circles. So if we look at motion at the very bottom of this thing, so let's say this is a loop-to-loop. And so you have, here's a bicycle, let's say. Have you ever tried to draw a bicycle? It's kind of weird. So there's someone going around, maybe it's a motorcycle or something, we don't care. But at this point, weight force is down, normal force is up, and it's larger because that's what's making you go in a circle. But what at the top? Well, at the top, the weight force is always down, but there's a second force. The normal force is also in. So the normal force doesn't have to be as big as it does here, because it has the weight force helping here and hindering there. And we can look at the side, normal force and the weight force. So what we can do is look at an arbitrary point, say over here somewhere, that makes an angle theta. And what we're going to have is this normal force and the weight force is going to be like that, and there's going to be an angle theta here. And so you can do sum of the forces in the y direction and x direction, but it doesn't necessarily make sense. We're going to make coordinates that move around the circle. So we'll say into the circle is positive circular coordinates, and then along the circle is positive tangential coordinates. So in the circular direction, you just have the normal force. The weight has components now. And so in the tangential direction, you have, you also have components of the weight. It's the adjacent, so it's the weight times cosine theta. In the tangential direction, you have the weight times sine theta. So we're not going, this is kind of notes more than it is a problem. What we're saying is, if you have a vertical circular motion, what you have is, actually this is in the negative direction. As you drive along the circle, as you go uphill, you slow down due to this bit. There's a portion that makes you turn and a portion that makes you slow down. This is the slow down or speed up. Because if you're on the other side, if you're over here, it's going to make you speed up. Then we have a portion that is turning. So this portion makes you go in a circle. So if you've ever been on a roller coaster, this is what you feel. At the bottom, you feel the most force because the weight is actively hindering you from going in the roller coaster. So the normal force is big. And as you go up, you lose weight, and at the top, you feel the most weightless. You still feel some weight because they're not going to let you get to zero weight here, or you fall off the track. But you can find an angle where at the wrong speed you fall off the track. It is possible to do that. Now, circles, if you've seen a roller coaster, they're not circles. They're actually this teardrop shape. And that's because if you go in a circle, you feel the forces change throughout the circle, and it kind of hurts. People get their neck hurt. They don't like it. So they make a shape that's more comfortable to the riders. And it's this kind of teardrop shape. It causes the forces to change at a more reasonable rate. Anyway, that's extra. So that's your vertical circular motion. And that's kind of where I want to stop.